Every ball game consists of four types of actions. In each game, they are known by different words, but they imply either the same or similar action. I have categorized those action verbs for the various ball games into four. The first one is to throw or hit or kick. The second one is to catch or to receive. The third one is to run. And the fourth one is to pass. So let's say that in football, I am able to master those four actions while I play. If I played tennis, I will know what actions I've got to perform, although I might not have the skill to do so in this new game. But because I am very good in football, at least I will be better off in understanding the game of tennis than someone who never ever played any game in his life. So the actions that I learned and mastered in one game would definitely help me in another game. Not only that, if I am an avid football player, even in my verbal communications, I will tend to use those four types of action verbs. I will say, throw me the answer. I can't catch what you said. Do you really want me to run over whatever you have just said? I can't answer this question. I pass. So you see that mastery or familiarity, at least, in one domain like football transcends or extends to other domains. While football was a physical domain, the action verbs and their usage transcended or extended to the mental domain of thinking and communicating here. Now, you might be wondering where I am getting at with this ball game concept. You must have guessed that it's an analogy to something that I want to talk about. That is correct. Now that we have established that thinking is like a ball game, and like there are many types of ball games, we have identified eight types of thinking. We understood how the various realms and components of mathematics affect the eight types of thinking. At this stage, it is not proven theory, but just an early hypothesis. Now, the next step I want to make is that even in the mental process of thinking, there are actions that we do, like in the physical domain, they can be summarized or represented into action verbs. Now, taking the earlier analogy still further, we learned certain action verbs and how to perform them in mathematics, which is a mental domain. Now, what I am proposing in the form of another hypothesis in this section is that the actions that we learn in mathematics are translated to the other mental domains, which include the eight types of thinking that we have just discussed. Here, I do not propose action verbs for each of the eight thinking types. My research hasn't reached that depth yet, but it will suffice to bulk all those eight types of thinkings into one single category, like I did all the ball games earlier, to zero in on the four types of action verbs that are associated with all the ball games. So the action verbs from mathematics that I postulate have influenced our thinking over the years, albeit unconsciously, are those listed in the diagram below. They are solve, simplify, analyze, calculate, model, predict, prove, apply, and finally integrate. I am sure that you remember those action verbs from school, college, or university. At that time, we thought that they were limited to the mathematic course that we had to pass. But as you can see in the diagram below, those action verbs transcend the mathematical domain and extends to our thinking processes. In the diagram, I have applied the thinking in science and engineering, where mathematics is the backbone. Also, I've applied it in day to day living. This is the most interesting part because most people never think that mathematics has influenced them in the domain of living. The first mathematical problems that we were given was to solve something. So we had to find the answer of an equation like 5 into 150 plus 5. That is the simplest mathematics, and it gets more and more complex, as we all know. This is a skill that comes in handy throughout our lives. Whenever we are in a problem, we just say solve it. Like we pull out various rules and definition theorems in mathematics to solve a problem in either science engineering or in real life. Our brain is now trained to find precedents, old rules, uh, some kind of logic to come to a solution. The more knowledge you have, the better the solution will tend to be. Could be a solution, a relationship problem between a married couple, or decreasing the drag in the wings of a super jet. The principle of the action is the same that we used when we were doing mathematics in high school. Just that the knowledge base, or the number of rules, definitions, properties, theorems, theories, logics increased dramatically over time. The next action verb is simplify. We did not have to find the answer or the exact results, but we had to cut down or beautify or downsize a big equation into a simpler form. In the field of engineering, this is very important because we have to reduce complex formulas, streamline experimental setups so that they become manageable for easier analysis. In day-to-day life, this skill of simplification comes in very handy when we summarize reports, emails. Also, that skill is very useful when we have to break large tasks into smaller ones. Next, in mathematics, we were made to analyze graphs and equation and explain what they meant. Now that's a very important skill for scientists when they have to analyze the data from experiments and to analyze why a machine broke down, or for a doctor to make a proper diagnosis. In our daily lives, this skill helps us to understand why a situation unfolded in a particular way and not in another way. It also helps us to understand advantages, disadvantages of anything. Basically, it's the fundamental action verb that we use in order to make any kind of decisions. The fourth one is to calculate. There are so many things we'll calculate it, from arithmetics to probabilities and combinations to the rate of change and so on. In science, we have to calculate the amount of fuel that is required for a rocket to reach the moon, for example. Even in chemistry, we need to calculate how much chemical we need to put in order to get a desired reaction. In real life, it's used more than we think. Whenever it does us a favor, we'll calculate whether it's worth taking the favor, and we also calculate the cost of paying back. Human beings are highly calculative people. We are honest to ourselves. We even calculate how much love we want to give to another person based on how much we are getting back from the person. The next action verb is model. Of course, it's not the lady that walks on the ramp that I'm talking about here, but even that lady model is in alignment with the use of this action verb model as used in mathematics. Here it means that a certain phenomenon in the physical world or the mental world is represented as an equation consisting of numbers and variables and relationships between them. The most famous model is, of course, E is equal to mc square. Yes, it's an equation, but it's also a model. If you compare it to fashion, then it must be the most beautiful lady walking on the ramp, demonstrating the best dress. So that equation is modeling the conversion of energy from matter. Now you can see its use in science and engineering right away. But even in day-to-day living, our minds engages in lots of modeling. We play out various scenarios in our minds. We put in various variables and visualize them. For example, a simple action like going to office requires some kind of modeling. There is the variable of traffic, weather, and the various probabilities like of an accident or a car braking that would factor in. So this is also a very model, but at the simplest level. On a bigger level, we could have models of how economies grow or go into recession. If you are in a relationship, you could have your own model of what makes a marriage last forever and what causes marriage to break down. The next action verb is to predict. Have you forgotten? We were made to extrapolate a graph into the higher x coordinates. Well, it's the same in the sciences, where we use the equation that we developed as a model of a phenomenon just earlier in order to predict the variables in the future. Of course, we'd be using algebra and calculus. In the real world, based on our model of the traffic, we would predict that on a particular day, at a particular time, the time for commute would be either 10 minutes, 30 minutes, or more based on the data from weather, Google Streets map, or a friend calling that there's a jam somewhere, your fuel gauge, and even maybe your gut feeling about a possible accident. Also, based on the model for marriages, we can predict whether a certain couple will stay married or divorce. Of course, this is just a prediction, and how events fall out, like you reach your office on time or not, or the couple is staying together or not, will describe the validity of the model that you came up with in your mind, and of course the prediction skills that you have. The seventh action verb is to prove. That was one of my most favorite problems. The answer was given, and all you had to do was to prove it. One of the funny problems that used to come is we all know that 1 plus 1 is equal to 2. But some kids would challenge others to prove that no, 1 plus 1 is equal to 0 or 3. Then, in the time where we did not have internet to entertain ourselves, bored kids in the boarding school used to derive mad kind of logic and pull rules from God knows where to prove that it was true that 1 plus 1 is equal to 0 or 3. In the engineering department and science department, proving is an essential part of any theory. Even the equation that we just mentioned earlier of E is equal to mc square was proven to work through the atomic bomb. But in the sciences, we are also open to be proven wrong if the model that we make doesn't explain the past phenomenon and predicts the future outcomes with a large margin of error. Similarly, in our day to day life, we are always pressed to prove one thing and another. We have arguments to prove, and then we pull out quotations from some great people. Either they are false or true. Among the most misquoted and widely quoted great personalities is Albert Einstein, which unfortunately I am also doing now, I think. But when the other party is involved, there tends to be a state where the equilibrium is reached and the limit for the outrageousness of any argument. But a normal proof requires evidence and also logic and basis that comes in the form of earlier philosophies or rules or ideas that have evidence of being true. So, proving is a very important part of our thinking. Then, in mathematics, we are told to apply the formula that we just learned in a certain situation, like find the area using the equation given of a shape that is not exactly a circle or a rectangle. In the science and engineering, that's a very important skill because not every problem that comes can be applied simply through simplification, but it will need some twerking here and there. It could be in the design of a beam or a bridge or even in the statistical analysis of a data set. In day to day living, we must learn to apply the life lessons that we learn or we are taught. For example, the theory might be to speak the truth and be kind, but how do we apply that? That's another problem. How do you speak the truth if a man passed by you and then another man came asking you where that man had gone because he had to kill the earlier man. So, how would you apply the earlier two principles of truth and kindness here? So, that's a bit complicated, and this is a skill in the mental domain that is very important, and that is a byproduct of mathematics. Finally, we have to integrate this ninth action verb. It's so important for both science and engineering and day-to-day life. And this particular action verb comes in calculus, where we integrate to find the area, effect, or work done by a certain equation on a graph from one point to another point that we call limits. But in the sciences, it's about integrating data from multiple sensors, synthesizing different disciplines into a complex project, and it's involved the same principle of integration, where we have to use that particular muscle of our brains to synthesize things. In real life, it doesn't have to be the integration of biology and mechanics to produce a prosthetic arm or an artificial heart. It usually is as simple as creating a new dish or coming up with a new picture from scattered information about a certain situation. So, in this way, in this section, I wanted to convince you that mathematics has transformed our brains. It has affected us in the way we think in various domains that we listed as 8 of them. Also, like in the various ball games, we perform 4 types of actions like throwing or hitting or kicking, followed by catching or receiving, followed by running, finally by passing. In our mental domain, we engage into at least 9 actions that are attributable to our studies of mathematics. Of course, our minds or brains are capable of many more actions that could be attributed to other subjects that we study. But for the purpose of this chapter on mathematics, the 9 action verbs that are listed offer a great starting point for this new postulate on how mathematics has been shaping the human brain. I am aware of it. This awareness has helped me think better, more effectively, and efficiently. I hope that by reading this section, you would have gotten the same benefit